Hi everyone. So in this video I am going to explain you about Hermitian operator. In the previous video I have explained about linear operator and also Hilbert space, inner product space. So today let us discuss about Hermitian operator. First you should know operator definition. Operator is the one when you operate on any function or vector it gives another function or a vector. So what is Hermitian operator then? An operator is said to be Hermitian if a cap adjoint, this plus symbol is nothing but adjoint. Okay, a cap adjoint or dagger also we used to call. So a cap adjoint is equal to a cap. When an operator is said to be Hermitian, if it is um, like a cap adjoint is equal to a cap. Adjoint of an operator is equal to operator itself, a cap. Now we have to show that Hermitian operator also represents an Hermitian matrix. So matrices, as we know, in case of matrices also the same properties holds good for Hermitian matrix also and for operators also. So let us define the Hermitian operator. A cap be an Hermitian operator with respect to orthonormal basis that is given by phi I. So phi I is what? Orthonormal basis where I is equal to 1 to n is represented by matrix A such that Aij, I through jth column Aij is equal to, it is a matrix Aij is equal to phi I A cap phi j. So its inner product is given by phi I comma a cap phi j. That is equal to, in the previous video I have explained inner product. So we can take the inner product of two vectors is what? Conjugate of it. So it is what? Conjugate of the inner product of two vectors. So we can take phi j comma a cap adjoint phi I. As we know, a cap adjoint according to Hermitian operator definition, a cap adjoint is equal to a cap. So we can replace here a cap with a cap adjoint, where the definition of adjoint operator has been used. Okay, that is a cap adjoint equal to a. Then this uh, definition goes like this: aij equal to phi I comma a cap phi I phi j comma a cap phi I conjugate, that is equal to, if we change the vectors phi j comma phi I by operating an operator that is Hermitian operator, then we can write a cap j I conjugate. Okay, so that means Hermitian operator is also involves transport and conjugate property. Okay, ij row row and jth column can be transformed into jth row ith column and conjugate of it. That is both transpose and conjugate also involved in Hermitian operator definition. Okay, this is the definition of Hermitian operator. There are some properties or theorems related to Hermitian operator. So the eigenvalues of a Hermitian operator are real. So we have to prove that eigenvalues of Hermitian operator are real. And another property or theorem is eigenvalues belonging to two different eigen functions are orthogonal. Okay. So let us first prove eigenvalues of Hermitian operator are real. Let psi be an eigenfunction of Hermitian operator, then eigenvalue equation is given by a cap psi equal to lambda psi. So this is what the eigenvalue equation. A cap psi lambda psi. A cap is a Hermitian operator operating on the function psi. Lambda is eigenvalue. Okay. Let us consider it as equation 1. Taking its complex conjugate, we have to take complex conjugate of equation 1, that is A cap conjugate psi star is equal to lambda star psi star. So equation 1 complex conjugate is given by equation 2. Okay. Then according to condition of Hermitian operator, the integral, that is minus wave function psi star A cap psi d tau is equal to A cap, we can take A cap outside, or integral A cap psi star psi d tau. That means wave function vanishes at minus infinity and plus infinity. Okay, that means psi star psi is equal to 1. This condition must also holds good. That is normalization condition equal to 1. So this is what Hermitian operator condition, that is given by equation 3. Integral of psi star A psi d tau, that is d tau is volume element, is equal to integral A cap psi star psi d tau. So using equation 1 and 2, eigenvalue equation 1 and its complex conjugate equation 2, equation 3 gives A cap psi is what? Lambda psi. Okay. So we can substitute here A cap psi with lambda psi in the equation 3. That we get psi star lambda psi d tau, and RHS side A cap psi star is psi star psi d tau we have taken. So A cap psi star is, this is A cap psi star is equal to psi lambda star psi. So equation 3 can be written with the help of 1 and 2. Then you can take lambda outside the integral, that is integral psi star psi d tau equal to lambda star integral psi star psi d tau. If we subtract these two equations, lambda minus lambda star integral psi star psi d tau is equal to 0. Okay, this means this integral is not equal to 0. As I said, psi star psi vanishes at minus infinity to plus infinity, that is normalization condition is equal to 1. Okay, condition of normalization. Then we are left with lambda minus lambda star, that is equal to 0. Hence we can say that lambda star equal to lambda. This is only possible when lambda, that is eigenvalue, are real number. This proves the theorem. So finally we have proved that eigenvalues are real, means lambda conjugate of lambda is equal to lambda. Lambda is what? Eigenvalue. Real numbers conjugate, if you take, they are real numbers only. That's why we can say that eigenvalue of Hermitian operator are real. Let us go for another theorem. Eigenvectors belonging to two different eigenvalues are orthogonal. So let A cap be an Hermitian operator, psi 1 and psi 2 be two eigenvectors of operator A cap. So here we have to take two eigenvalue equations. Lambda 1 and lambda 2 are distinct eigenvalues of operator A cap corresponding to psi 1 and psi 2 respectively. Then eigenvalue equations are given by A cap psi 1 lambda psi 1, a cap psi 2 is equal to lambda psi 2. Two eigenvalue equations we have considered. Earlier we have considered only one eigenvalue equation. So here we have considered two eigenvalue equations. Let us take it as equation 1. Complex conjugate of the equation 1 we have to write, that is a cap star psi 1 star is equal to lambda star psi 1 star, or else we can also write a cap star psi 1 star is equal to lambda 2 psi 1 star. So a cap star psi 2 star is equal to lambda 2 star psi 2 star, or a cap star psi 2 star is equal to lambda 2 psi 2 star, because lambda 2 why we have taken lambda 1, it is lambda star is equal to lambda. We have proved in the first theorem lambda star equal to lambda. So we can take lambda 1 star is equal to lambda 1, lambda 2 star equal to lambda 2. Being lambda 1 and lambda 2 being eigenvalues of Hermitian operator which are real according to general condition of Hermitian operator a cap, the integral. Earlier only one equation we have considered. So here according to condition of Hermitian operator, integral of psi 2 star a cap psi 1 d tau is equal to a cap star psi 2 star psi 1 d tau. So using 1 and 2 we get psi 2 star lambda 1 a1 psi 1 we can substitute with a1 psi 1 is what, lambda 1 psi 1. So lambda 1 psi 1 d tau, and RHS side a star psi 2 star psi 1 we have written. A star psi 2 star is what, lambda 2 star psi 2 star. So lambda 2 psi 2 star psi 1 d tau. Then take lambda 1 outside the integral, and this is what normalization condition. Psi 2 star psi 1 d tau is equal to lambda 2, or you can take outside the integral psi 2 star psi 1 d tau. Take this equation on the LHS side, we can write lambda 1 minus lambda 2 integral psi 2 star psi 1 d tau is equal to 0. Here lambda 1 and lambda 2 which are not equal to 0, then we can say that integral psi 2 star psi 1 d tau is equal to 0. This implies eigenvectors belonging to two different eigenvalues are orthogonal. So these are the two important properties or theorems related to Hermitian operator. So first we should define Hermitian operator and then we can explain their properties. Eigenvalues of Hermitian operator are real. Eigenvectors belonging to two different eigenvalues are orthogonal. I hope this